So this is the second lecture in the what you call image enhancement in frequency domain. We will consider today the Fourier transform of sampled functions. So if you have a continuous signal like this, then if you sample it using a pulse train or train of impulses, as it is known as impulse train or train of impulses, then after sampling we'll get the function which is something like this. And the points associated with that will come out to be like this. And we can try to write the f of t is equal to f of t, this sampling train multiplied by the sampling train. This is f t, and this is the what you call impulse train, whatever we have, which is the sampling function, and that gives us the value of n equal to minus infinity f t del of t minus n del t. So if we take the what you call Fourier transform of f of t, then naturally it is going to become the two different functions. Then that will give the convolution of the corresponding Fourier transforms. So S of mu is this function which is 1 by del t sigma of n equal to minus infinity del of mu minus n del t. This is the Fourier transform of the what you call impulse train, right? And the Fourier transform of f of mu, the function f of t, which is f of mu, which has to be considered. And here we try to write the convolution, something like this, and 1 by substitute for the value of s of mu minus tau del tau from here, right? And that will be 1 by del 2 tau as it is, because here it is mu minus tau. In place of this mu, you have mu minus tau over here, n by del t as it is. And if you take this, if you simplify it further, you can just exchange the sigma and the integral, and you'll get this. And this term, which is nothing but integral of f of t del of mu minus tau minus n del t of del tau will be equal to f of mu minus n by del t. F of mu minus n by del t, because here we have tau and here we have tau, and that will go off, and that's why it is f of mu minus n by del t. So we have already said this, the Fourier transform of a sampled function will turn out to be a discrete function. So here we consider, whenever we consider the sampling of Fourier transform of sampled functions, we consider only band limited signals. Band limited signals are those which are restricted to a finite frequency range. So band's limited signal is a signal whose Fourier transform is 0 above a certain finite frequency, or we can say that they are within a finite frequency range. Okay. In other words, if the Fourier transform has finite support, okay, it just means that it is Fourier transform has finite support, means it is within a finite range of values, then the signal is said to be band limited. So an example of a simple band limited signal is xt is equal to sine of 2 pi ft into theta, where the frequency is only single frequency f. Okay, this is a sinusoidal frequency, single frequency f. Now, if we have the what you call Fourier transform of ft to be band limited like this, okay, within the band minus mu max and mu max, okay, this is band limited like this, then if you sample that function, then we are going to get like this. If we have oversampling, oversampling just means 1 by del t is much greater than 2 mu max. 1 by del t is much more than 2 mu max. So this is mu max, 2 mu max will turn out to be somewhere here, might be, but this 1 by del t is greater than this 2 mu max. Okay. So that means the value from here to here, center to center might be, or the value from here to here is greater than the 2 mu max over here. However, if we have critical sampling, then that is 1 by del t is equal to 2 mu max, then if both are same, that is this length and this length are same, then we are going to get this type of critically sampled signal. But however, if it is undersampled, if 1 by del t is less than 2 mu max. That is 2 mu max is, greater than 1 by del t. And that is the case which is appearing over here. You see that we are not able to reproduce the whole of the signal. So this part comes out here as it is. This part comes out here as it is. But only this part is coming here. Okay. That is the lower frequencies are not appearing over here. Lower frequencies appear as high frequencies when we do undersampling. Lower frequencies, this is lower frequency, will appear as high frequency in the undersampling. So we can recover f of t from its sample version if we can isolate a copy of f mu from the periodic sequence of copies of this function containing f hat mu, the transform of the sampled function f of t. That just means that if we have, this is your, f hat mu, this is also f hat mu, this is f hat mu, you can get back this signal by just, what you call filtering out only this portion or filtering out only this portion. From here and here, you can get back this. But from here, you can't get back this because even if you filter that, then you'll get the function which is from here to here. So that means frequencies which are here will not be able to appear there. So reconstruction is not possible if we have 1 by del t less than 2 mu max. That is what it means, and that is the sampling theorem. Okay, so we can recover ft from its sample version if we can isolate a copy of f mu from the periodic sequence of copies of this function contained in f of mu. The transform of the sample function f of t. Sufficient separation is guaranteed if 1 by del t is greater than 2 mu max. So we have sufficient separation if we have 1 by del t greater than 2 mu max, and that is the, so to say, the case of in the earlier figure oversampling. Okay? The case of oversampling. So from this, we get the sampling theorem. A continuous band limited function can be recovered completely from a set of its samples if the samples are acquired at a rate exceeding twice the highest frequency content of the function. So this is the twice of the highest frequency component, and if this frequency is, so to say, is greater than the twice the frequency over here, then we can get back the function. A continuous band limited function can be recovered completely from a set of its samples if its samples are acquired at a rate exceeding twice the highest frequency content of the function. Okay, if this quantity is greater than twice of the highest frequency component in the function, then we can recover it very easily. And that's what is shown over here. And we have here, what you call the sampled, so to say, Fourier transform. And to that, we put just a, filter it using a band pass, a low pass filter or a band pass filter, whatever you call it. This is really speaking a low pass filter because 0 to some frequency we have, band pass will be somewhere here, right? So this is a low pass filter. And within from that low pass filter, you can just extract it. However, most of the time, we can just put a band pass filter. Okay, band pass filter for a band limited signal, and you can just extract it over here. So this is the filter which we need to use to get back this value, and that is possible because the figure is like this, wherein 1 by del t is greater than twice of mu max. So extracting one period of transform of band limited function using an ideal low pass filter is considered over here. So f of t is integral of minus infinity f of mu e to the power of j2 pi mu t del mu. So what is this? This is just a ideal low pass filter. So if a band limited function is sampled at a rate that is less than twice its highest frequency, so till now we said we can get back the signal if the 1 by del t is greater than the twice the highest frequency. If it is less, what happens? We say that aliasing occurs. Okay. If the band limited function is sampled at a rate that is less than twice its highest frequency, we say that aliasing occurs. Now, whenever aliasing is there, the inverse transform will yield a corrupted function. Okay, whenever we what you call have the sampling rate which is less than twice the highest frequency, then we cannot recover the original image. We cannot recover the original image means the inverse Fourier transform of that you will have a corrupted function. This effect is known as frequency aliasing or simply as aliasing. So if you have the 1 by del t lesser than 2f max, not greater, so this is lesser than 2f max, okay, that is what we might have written here. Okay, 1 by del t lesser than 2 mu max, and that's the figure at this point. And then if you try to filter that using again a band limited function, then definitely okay you will not get back the original value, because this is not the one which we had. The one which we had was like this. Okay, the one which we had was from here, it is like this to like this. Okay, so the higher frequency what you call component at this time is should not appear, but appear with lesser value, but it's appearing with what you call more magnitude. So we cannot just not possible to record. For a transform of an undersampled bandwidth function is what we have here, and the ideal low pass filter is used over here. The product of A and B, we will see that the interference is there in the figure. So what does it mean? The undersampling function looks like a sine wave having a frequency much lower than the frequency of the continuous signal. So the undersampling will give us a frequency which is much lower than the frequency which is present in the original signal. Okay, so this just gives us the del t value. So this we will get the envelope of the same. So function reconstruction from sample data, f mu is equal to h mu into f hat mu, and ft will be equal to the inverse of Fourier inverse of the f mu, and that will give us the h mu f hat mu. And if you what you call have the Fourier transform of this, then it multiplication in the frequency domain will be given by the convolution in the what you call time domain, and this convolution in the time domain will just give us the n is equal to minus infinity to infinity f of n del t sinc t minus n del t by n del t. This we can derive. Okay, this we can derive. Then we come to the discrete Fourier transform of one variable, which is a better representation for discrete quantities. So f of mu is equal to x equal to 0 to m minus 1, f of x e to the power of minus j 2 pi mu x by m, where mu is equal to 0, 1 till m minus 1. F of x again is 1 by m sigma mu equal to 0 to m minus 1, f of mu e to the power of j 2 pi mu x m, where x is 0, 1 to m minus 1. So these are the discrete Fourier transform of the one variable, but representation might be a little different. 2D impulse and shifting property for the continuous function. If you have an impulse function, it is a two-dimension value, then we will have the double integral of that value turning out to be 1. So if you shift it with respect to that, that is f of t comma z del t comma z dt gz, then that will be f of 0 comma 0. And if you take here t minus z del of t minus t naught z minus z naught dt dz is equal to f of t naught z naught. So we are just trying to extend the one-dimensional quantity into a two-dimensional quantity over here. Okay, earlier if we had f of t del of t dt, then we would have written f of 0. But now we have tz del t del z, then f of 0 comma 0. If this was f of t del of t minus t naught in a one-dimensional case, then this will be f of t naught. Because we have two variables, we are extending it to f of t naught comma z naught. Now, if you take a discrete case, that was a continuous case. Whenever we talk about continuous case, then this will be infinity at t equal to z equal to 0 and 0 otherwise. And then we'll have, whenever continuous case is there, we'll have integration. Whereas in a discrete case, when we have an impulse del of xy, then that will be equal to 1 if x equal to y equal to 0 and 0 otherwise. This will no more be infinity. And in that case, the shifting property will just give us the summation of the quantities. Double summation f of xy del of xy will be f of 0 comma 0, and double summation f of xy del of x minus x naught y minus y naught will be f of x naught y naught. Similarly, the 2D Fourier transform can be represented by this in a continuous case, f of mu v with the values, and the continuous case will be here. 2D function is a 2D function is given over here. A section of its spectrum can be mentioned in the equation over there. Okay, this is the figure whose expression is written like this. So f of mu comma v is just the 2D Fourier transform of f of t comma z, and that's what we have written here. Okay, f of t comma z, Fourier transform of f of t comma z is f of mu comma p. Okay, so f of mu comma v is this function, and this turns out to be, we'll have the double sinc function. So double sinc function just means in the 2 dimensions we'll have the sinc function, and that will look something like this. Okay, so both in the x dimension as well as in the y dimension, this is v dimension and x dimension, both dimensions we have the sinc function. So a section of its spectrum not to scale, the block is longer than along the t-axis, so the spectrum is more contracted along the mu axis. Along the mu axis, it is more contracted and longer in the t-axis. So we can consider the 2D impulse train similar to the 1D impulse train, and the 2D impulse train is something like this: sigma sigma del t minus m del t, comma z minus n del z. Okay, in a single case it will be s del t t. At that time we'll have only a single summation del of t minus m del t. That's all. Yeah, z minus n del z will not be there at this z term. This z term are not there, and hence one of the summations will not be there also. So in a 2-dimensional case, we will turn out that the 2-dimensional impulse train will look something like this. So this is the one which is used for sampling a 2-dimensional function. So corresponding to the 2D sampling, we have the 2D sampling theorem. Function f of z is said to be band limited if its Fourier transform is 0 outside the rectangle established by the intervals minus v max, comma mu max, and minus v max, comma v max. That is, f of mu v is equal to 0 for mu greater than mu max and v greater than v max, greater than or equal to mu max. So it's band limited. Band limited just means within the range of mu max and v max in the 2 dimension. So under that condition, the 2-dimensional sampling theorem indicates that the del t should be lesser than 1 by 2 v max and del z should be less than 1 by 2 v max. Or inversely speaking, 1 by del t should be greater than the 2 v max and 1 by del z should be greater than the 2 v max. So a continuous band limited function f of t comma z can be recovered with no error from a set of its samples if the sampling intervals are mentioned over here. So sampling interval, please remember, is exactly the opposite of the sampling frequency. Okay, 1 by delta is frequency, delta is the sampling interval. So as soon as you take 1 by this sign, all the what you call uh, you know, inequality also will go from lesser than to greater than. Here also it will go from greater than to uh, lesser than to greater than if we take 1 by del z or 1 by del t. So the 2D sampling is how it looks like here. 2D, two-dimensional Fourier transform of a oversampled figure will be like this. Undersampled, you know, band limited function will be like this. So where there's a little overlap here. Okay. Critically will be just, you know, this point touching this point touching this, and this point touching this, and this point touching this. So this is oversampled, wherein you can separate each one of this very easily, or rather, this is the one which we want. We can separate it through a ideal low pass, you know, box filter of 2 dimension. Whereas even if you separate this, you will get some sort of aliasing because you have overlap here, you have overlap here, you have overlap here, you have overlap. And if you use a band, you know, pass filter, or so to say ideal low pass box filter, ideal low pass box filter, then it will not be able to get back the original signal, recover the original signal. So whenever aliasing occurs in images, how does it look like? So in an imaging system, the number of sample is fixed at 96 into 96 pixels. If you use this system to digitize the checkerboard pattern, then this is how it looks like. So aliasing in images, in A and B, the lengths of the sides of the squares are 16 and 6 pixels respectively. Aliasing is, you know, negligible. In C and D, the sides of the squares are 0.9174 and 0.4798 respectively, and the results show significant aliasing. So A and B, you know, aliasing is not there. It look as if no aliasing is there. Whereas in C and D, you can see that, you know, you have a little sort of aliasing. But however, we feel that the, you know, what you call D looks like a normal image. But really speaking, it is not so. Really speaking, we have aliasing in this figure also. That is because the points are shifted from one to the other. So you can see that, you know, you have a block here and a block here. You have a block here and you don't have a block here. So you have an extra thing over here, and hence we feel as if, you know, it's a normal image. It's not a normal image, whereas aliasing is clearly visible in this figure. So undersampling is what we are doing for this, and oversampling for this. Another way of, you know, illustration of aliasing is a digital image with negligible visual aliasing is shown over here. Results of blurring the image in A, whatever is there here, you know, is blurred, and we get this. Then C, but aliasing is no longer, you know, C is what you call results of blurring the image in A with 3x3 average filter prior to resizing. The second one is result of resizing the image to 50% of its original size by pixel deletion. Aliasing is clearly visible in this. So a little you can see here, a little aberration here and here and here and here and all that. Okay. So in the C, result of blurring the image in A with 3x3 average filter prior to resizing, the image is slightly more blurred than B, but aliasing is no longer objectionable. So you can see that aliasing is no longer objectionable. You don't have this kind of what you call figure, and compared to this, you know, this is more smoother because we are just trying to blur it. Similarly, we have here also another figure, a 1000 into 1024 digital image of a computer generated scene with negligible visible aliasing over here. Result of reducing A to 25% of its original size using the bilinear interpolation is this figure, and results of blurring the image in a 5x5 averaging filter prior to resizing it to 25% using bilinear interpolation is shown over here. we'll take up the Moray pattern in the next class.